Data Skeptic features interviews with experts on topics related to data science, all through the eye of scientific skepticism.
Hui Xiong has a PhD in computer science from the University of Minnesota Twin Cities and is currently a professor and vice chair in the Management Science and Information Systems Department. He is also the director of the Rutgers Center for Information Assurance, an ACM Distinguished Scientist, and a senior member of IEEE. Dr. Xiong's general areas of interest are in data and knowledge engineering, with a focus on developing effective and efficient data analysis techniques for emerging data-intensive applications. His recent work, Rebalancing Bike-Sharing Systems, a Multi-Source Data Smart Optimization, was presented at the KDD conference earlier this year. And it's this paper I invited him here to discuss today. Hui, welcome to Data Skeptic.
Thanks for the introduction.
So maybe to begin with, could you tell us a little bit about bike-sharing systems and what this rebalancing problem you're trying to solve actually is?
Nowadays, in big urban cities like New York City or Chicago or Los Angeles, and also some other big city in Europe and Asia, we have this we so-called bike sharing system. So the purpose is to try to provide some missing links in public transportation system. Essentially, in those cities, we will have a lot of stations. Those stations will provide the bicycles available for passengers to use. The key purpose for this bike sharing system there's a key issue is try to effectively rebalancing the operation. The idea is very simple. Actually, during certain time period, for some station, say for instance in the New York City, during the morning time, for some station, many people will take the bicycle and ride to some other stations, and very soon those stations will be run out of bicycles. For some other stations, they will not have enough dock available to put all these bicycles. So in this case, some station they short of bicycle, and some station they will have too many bicycle available there, and people cannot even put their bicycle to that station. So in this case, we will have this rebalancing operation, try to bring the bicycle from the station they already have too many available there to the station they don't have any bicycle available. So this we call the rebalancing operation. In order to make this system to work effectively, this rebalancing operation is happening every day to make the system more effective for people to use.
Interesting. So the bikes rebalance from station to station. I know this, the work you and your colleagues did, this is new work, at least it's new to me.
Yes.
But bike share systems have been around for a while. So how was this problem solved historically?
In the history, we do have this problem called the inventory rebalancing problem. However, this problem is quite different. We do have several challenging issues. The first is, say for instance, in New York City, we have more than 300 stations available. So in other words, this is a very large scale dynamic inventory optimization problem. There will be second challenging issue is demand for this dynamic inventory rebalancing. It's not like a traditional way people doing this inventory rebalancing. We deal with some very static case. So basically, we hope this can be more frequently happening every day. Also, another big challenge is usually for the inventory rebalancing, they have the assumption there's no we so-called outlier station. So outlier station means for some station, their demand is so huge. This demand cannot be satisfied by rebalancing operation. So in other words, we needed to do this dynamic rebalancing with the existence of all these outlier stations. Actually, we do have the opportunity nowadays try to make this rebalancing optimization happening. It's because of now we have a large scale of historic data. So in other words, now it's possible we completely use a data-driven approach, and so always so-called big data approach, try to do this data-driven based optimization. This is one major difference from traditional way we do this rebalancing optimization problem.
So I definitely want to get into some of the specifics of the optimization, but for the moment, let's maybe just stay at the high level and assume you have the problem solved. That is, you know exactly which bikes need to move from station A to station B. Once you have that optimized plan in place, how is it carried out?
In New York City, say for instance, they have 8 to 10 chunks, and they routinely move in those bicycles around. So basically, our research is try to develop some optimized strategy. So help them try to schedule these rebalancing efforts more optimized way. So say, for instance, we help them how actually they can allocate their resource, their chunks, and also try to make some plan for the driving routes and also help them for the scheduling for those kind of delivery.
I see. So the service trucks move the bikes from station to station to rebalance, and your optimization allows them to do so more efficiently. So if people working in New York City on the bike sharing system haven't read your paper yet, maybe one naive thing they might try is go to the station that's most full, has the most bikes, and then take them to the most empty statement and drop them off there, and then just repeat that process. Why would that be a poor solution?
You mean the passenger do this?
The trucks.
Oh, okay. Right now, the trucks, they can do this more like there's no guidance. So in other words, we have more than 300 stations available there. For the common case, right now they are doing is they based on their experience. Say, for instance, they may receive the phone call or they may have those kind of demand and try to, say, for instance, station A, they receive the phone call, say station A run out of bicycle. Then they try to say bring some bicycle from the nearby station and to be that station. However, those decision is purely based on the experience. There's no guidance from all these different we so-called the data or fact. So our purpose is just say we try to understand the complete situation for every station. Say, for instance, we know exactly for every station how many bicycles are available there, and also we make the prediction in the next time period. So how many bicycles available in each station? We based on the current situation and also based on our prediction result, and we can do this optimized solution. Try to schedule, say, for instance, for those 8 or 10 chunks more effectively. In this way, we can make the most use of all the bicycles available in the system.
Yeah, I can see where having a prediction is much better than waiting for a consumer complaint when the problem's already arisen. It makes sense to me that that's a big improvement. You had mentioned considering time. I can definitely see how weekdays versus weekends would have very different usage patterns and behaviors. Are there other factors you considered in formulating your predictions?
Actually, there's a key point in the paper. Our prediction, say, for instance, we predict the pickup demand and also drop-off demand for each station. And we actually consider about the unique characteristics for this bike sharing system. Typically, the people use bicycle is affected by the weather condition. When we try to develop this prediction model, try to predict the pickup demand and the drop-off demand for each station, we consider about the weather data. Say, for instance, we consider about the weather similarity between different time period and also the raining days, snowing days, and also we consider about the wind. If very windy and not many people will use the bicycle, and also consider about the other weather condition. So in other words, we consider temperature and wind and humidity, and those information we use try to capture different similarity. So in other words, we look at the historical data. For one station, if we try to predict the pickup demand for the next hour, and we will look at the historical data, we try to capture top K, most similar weather condition. Then we try to use the demand in those periods as the prediction result for the current one.
Oh, that makes sense. Yeah, I can see where weather would be very important. I'm less inclined to ride in, rainier, inclement weather, things like that. It's not totally clear to me how you would compare the similarity of these two things because you have, 4 different dimensions. Could you talk about how you formulate weather similarity?
We consider about the 3 types of similarity measurement. One is the weather similarity. The second one is the temperature similarity, consider about the temperature similarity. And also we consider about the humidity, wind speed, and also the visibility similarity. All this information we extract from the weather report, and they associated with different location and the time. We will aggregate all this similarity measurement into one linear combination, and we try to learn the parameter combined for each factors.
Yeah, weather's a very novel and probably a very smart thing to include in the model. I'm looking right now at figure 3 in your paper. This being an audio podcast, I'll have to tell listeners to go to the show notes where they can get to your paper and see these figures as well, but I'll describe it for those who can't. These figures are really intuitive. They describe how weather affects ridership. For example, I can see how as humidity increases, ridership decreases, and that makes perfect sense to me. I was surprised, though, at temperature. there's a point of discontinuity around maybe it's 48 degrees Fahrenheit in figure C, where there's a jump, like a plateau. Do you have any insight into what that is or why people are behaving that way, instead of a more like continuous gradient type of change?
Yeah, we actually noticed these things before. There might be several issues cause these things happening. One thing is we might have some missing data in the data we collect. That's one thing might cause these things happen. However, because our prediction is based on these combined multiple factors, so even one factor, they have some missing data and or some noise, it will not impact too much on our combined prediction result. Overall, our prediction result is still very accurate.
Makes sense. I think one of the strengths of your approach is that it's data-driven. So I was wondering if you could tell me a little bit about the raw data sets you have available. Where does your data come from?
We have multiple data sources. One data source certainly is the data from bike sharing system. This data can be publicly available, and because they provide API, so actually if you work with the API, you can actually have this data feed in a real-time way to get all this data. So we have the location data for each station, and also we have the demand information from every station. Say, for instance, we connect to the API, so every 5 seconds we actually can read the data, so you exactly know how many bicycles available in each station. And also we get the access to the weather report for the New York City, so we have the weather data as well. So all this data we can have from the public domain.
Very interesting. So I assume you have information about the stations. We talked about, how many open slots there are and things like that. But I'm curious about what you know about the individual rides. For example, if I went to a particular intersection and got a bike and went to a different place and dropped it off, would you know that transaction level data about me?
So it works this way. For some bicycle rider, they have a membership, but we don't know exact which rider actually take the bicycle due to this anonymization issue. But they do have an ID. This ID cannot be linked to anyone, but this ID can indicate, say, for if you have membership, so we know you come back. But if you are random passengers and using the system, we are not going to link to you come back to system or you just appear once. This system first is purely anonymized. We do have one ID associated for every usage. However, if you have a membership, so we might be know you come back. If we don't have a membership, we may not know you come back again.
I see. So I know a few people who are working in New York City and they're cyclists and they use that in their commute to go either from home to work or maybe from their subway stop to work and then back again at the end. I would guess if they do it every day, they're very efficient and direct, which is easy to model. But there's also tourists and exercisers who have very different behavior. How do these different types of users affect your model?
Yes, and actually these are very interesting for help us to predict our demand and the pickup as well. If for some station, the usage most coming from the people living around, their usage pattern is more regular. If the usage pattern for certain station becomes more regular, then the prediction for those station becomes more accurate. In other words, we use this result for rebalancing efforts will be more effective. However, for some station, the most usage is actually coming from the people who traveling to the New York City, or they just come there for random use. So in this case, the usage for those stations becomes not so regular. Then in other words, our prediction result for those stations becomes less accurate. In other words, if we use this information for our rebalancing efforts, then our rebalancing will becomes less effective.
So every optimization problem has an objective function you're trying to optimize for.
Yes.
What are you trying to optimize for in the rebalancing problem?
Let me first introduce our rebalancing strategy from a little bit higher level. So this is a very challenging problem. First, we have more than 300 stations. So this is a very large scale rebalancing efforts. If we using the traditional way to do this rebalancing optimization, the problem is infeasible. Infeasible means if we use all this data together, all these stations together, we cannot find the optimized solution. So instead, we have a new strategy to doing this. We first doing the clustering. We try to group the older station available in the New York City into, say, for instance, 8 or to 10 clusters. Based on a lot of usage pattern, we divide them first. For each cluster, then we assign one chunk. So in other words, one chunk only responsible for rebalancing operation within one cluster. So in other words, this bicycle will not go all the way to all the New York City. They only stay in one region. Try to coordinate all these rebalancing efforts for all the stations available in this area. This way, we reduce a very complex problem. It's more like a divide and conquer. We try to reduce a very complex problem into some small problem and it becomes feasible. In other words, it's possible for us to find the optimized solution within this region.
Makes sense. And then one truck per region, I suppose. But I assume there must be some additional constraints. For example, trucks don't have an infinite space. What are the other constraints you have to deal with?
Because every trunk, they only have limited capacity. So there's another thing I just mentioned in the beginning. So there's another big challenge is outlier station. They have a normal demand is go beyond any trunk can be satisfied. So in other words, for all these outlier stations, we first need to identify and then remove those outlier stations. In other words, our optimization system will not be work due to the existence of this outlier station. So we will first remove all these outlier stations. Otherwise, the optimization cannot be done.
When you have that clustering solution in place and each truck has been assigned its jurisdiction area, is it then a bit like the traveling salesman problem?
Actually, it's more like a divide and conquer. We try to divide a very big complex problem into several small problems. For the big problem, like large-scale station rebalancing problem, becomes infeasible. We cannot find the optimized solution. Then we divide this big problem using clustering technique into some smaller one. Then within each cluster, then we can find the optimized solution for the rebalancing efforts.
Gotcha. And then within those clusters, what are you trying to minimize or maybe maximize over for each truck? Is it, minimize the fuel usage or the time?
Basically, we try to minimize the movement for the trunk to do and also try to make every station within the area becomes more available for the user request.
That's interesting. So am I correct in saying that the goal is to keep the stations at a balance between supply and demand?
Right, and also try to help the trunk to travel less and to move more effectively.
So it seems like a pretty complex system, the whole bike share system. Even as the trucks are out there executing a plan, different cyclists are still getting and returning bikes at stations. It's always changing.
Right.
What are some of the added challenges that arise from the dynamic nature of this problem?
Actually, that's the key from traditional inventory optimization problem. This is more like a dynamic inventory optimization problem. That's why the dynamic prediction for the station drop-off demand and the pickup demand becomes very important. That's why we have this prediction model used in the system. So in other words, so our estimation for the demand is actually based on the prediction result for every dynamic time period.
So I also wanted to ask about the clustering approach you took. I think it's a smart thing to do to help take an intractable problem and make it tractable, but I was wondering about certain geographic features or maybe urban features like one-way streets that might affect this. For example, could you be overlooking a good plan that runs, down a long north-south street and not consider it because its centroid would look less efficient than a more dense cluster?
Yes, so when we do the clustering, we actually consider about all these geometric factors. Say, for instance, we consider about the location information. First, we try to group the station nearby together. If we group all these stations nearby together, then we can help the trunk not to move far away, just move nearby, and this will be more effective. And the second, we consider about all these stations, how actually they are transfer their bicycles. Say, for instance, some stations, they have more highway connection. Say, for instance, a lot of people simply during the morning time, they will travel from station A to station B. So all this connected usage information will also be used when we do the clustering.
And is the clustering a one-time solution that the trucks will use for, presumably forever or for a while, or do you need to regularly recluster?
Right now, we're doing this one-time solution. However, if we notice a highway usage change, say, for instance, if the people change their usage pattern quite significantly, we might change our clustering result slightly.
Your approach includes many useful subsystems, such as the demand prediction and the interstation bike transition function. Could you describe the general architecture of how all these things fit together?
In terms of general architecture, it's actually not that complex. Basically, we're starting from the data. We have the weather report data, we have the trip records data, and also we have station status data. These three types of data source will provide all this data information to us. Then based on the weather data, we develop this similarity measurement. All this similarity measurement can help us to build a prediction model to predict the pickup demand. Based on the station data and also the trip records data, we can build this bike drop-off demanding prediction. Then eventually, based on the pickup demand result and also the drop-off demand prediction result, we can actually build this stational inventory target level result. Once we have this result, we can fit into the clustering result. So basically, in parallel, we already do this clustering beforehand. So once we divide the whole New York City, say like more than 300 stations into like 10 clusters, we can feed all these prediction results into each cluster. And then, of course, we already remove all these outliers. Then we can, based on our prediction result, try to optimize our rebalancing efforts, try to make the suggestion for the planning for the trunk can move around, how actually they can move around at a different time period.
So your approach depends on good pickup and drop-off demand predictions.
Yes.
How does it perform on the training data set you have available?
If we do not consider about this prediction result, we just say using the approach we just introduced, we do the clustering, we divide the area, the station into different groups, then we try to using traditional optimization strategy based on the current status for each station, then the result is much worse than we consider about this dynamic prediction.
And in terms of measuring the performance of your system, how do you go about calculating that?
So basically, as we described, our approach, we have several unique perspectives. First, we consider about the impact from the outlier. We illustrate in our validation, if we have all these outlier stations, in other words, their demand becomes an extremely large value, a normal value, and the existing trunk cannot be satisfied. If we remove this outlier, our solution becomes more tunable. So we first illustrate the impact from outlier. So in other words, we must remove this outlier before we can do any this rebalancing operation. The second validation, we try to validate the importance for this dynamic prediction for different pickup stations and also drop-off stations. After we add in this dynamic prediction for the drop-off prediction and also pickup demands, and we can actually improve our result significantly.
The paper has some really promising results. Since its release, has New York City shown any interest in implementing your methods?
That's one thing we have in mind. Right now, we just use historic data and try to validate the effective of the strategy. However, it will be more important and also becomes more practical if we can work with Citibank company and try to deploy the system and see how it works in a real world situation.
Yeah, that would be very exciting.
Right. And actually, we have been trying to contact with them, and also I send the paper to them and see whether they can use our strategy in their system.
Well, very cool. I hope something actually ends up coming from that.
Yes, and that's the goal for our research work. Even we're doing this fundamental research because we are from university, we're doing this non-profit research. However, from my own perspective, I try to use this real-world data, try to solve real-world problem. I hope in reality the company can use our strategy and at least try and in their system.
One of the things that excited me about your work is that it's based entirely on open data. So I could get access to the same things you have. I could reproduce it.
Right.
Perhaps I could improve it. And the city could benefit from all those improvements with no added cost to the taxpayer outside of making the data open.
Right, and this research and also can be validated by many other researchers because all this data is publicly available, and also our strategy and our approach becomes very informative in the paper, and the people can repeat our experiments and also can actually implement our strategy. In my research group, I have been working for different types of problem. The solution to this problem, actually, we leverage the experience from our many other data-related projects. For data mining practitioner, it's extremely important to study from the real-world problem and also the real-world data, and eventually come up to the solution, and which can be repeatable and also can be implemented by the industry or other researchers. This actually, I believe, has a lot of meaning to the society and also to the industry.
Absolutely. Maybe to wrap up, could you mention some of the other projects your research group is working on?
Yes, certainly. Recently, The Economist You know the Economist magazine, right?
Definitely.
The Economist magazine, there's one journalist that interviewed me, and they published another KDD paper. And so basically, in the Economist, they featured one of our research work, and also published at the KDD 2016. For that work is we develop one methodology. It's also based on the data available in the public transportation system. We use those data for the passenger travel in the public transportation system, try to identify pickpockets.
Ah, yeah, the pickpocket paper. I saw that. I have not read it yet, but it's at the very top of my list. I'm excited to go through it.
That's an interesting one. And also, I have been working on another major effort is for the people analytics. I'm not sure you're aware of this area or not.
I am not. Tell me a little bit about it.
For the people analytics, it's unlike a traditional way people doing this human resource. For traditional way people doing human resource is purely, put this way, it's not data driven. So in other words, it's very subjective. We want to develop some talent intelligence system is purely based on the data. It's data driven. So in other words, our decision can be very objective, and also will be more scientific oriented. And also our approach will be more transparent because we base on all the complete information available. For the traditional people doing human resource decision, they base on very fragmented information. In other words, the information for decision making may not be complete. We will want to develop the talent intelligence system is purely based on the data, and also the information will be more complete. I can give you one example. Say, for instance, for the staffing, how actually we can recruit the people. So basically, we can try to answer the question based on the historical data. We try to predict which person is a better candidate for certain types of position. We can do the matching between the talent and also the job positions. So this will be matching based on the predictive modeling. And also we can do many other things like we identify like the kids just graduated from the college. We identify which kids will become more successful in the company. So in other words, we can identify some employee star before they become a star. Another thing we're doing is we try to understand how the employee, like a star employee, will leave the company. Say if we try to make the prediction and which employee are going to leave. If this employee is leave the company, do we have enough talent pipeline available for this position if this person leave? All this human resource operation can actually be developed based on the data. We have new ways to collect all this data. Say, for instance, in the big company, we have all this ERP system becomes available. And also we have a lot of system available for our information about our employee, about routine operation management, and also many decision making. So all this information system allow us to collect a huge amount of information about the talent. So based on this information, we can develop this talent intelligence system. This system can eventually help us to do a lot of this management decision, like staffing, compensation, and the benefit, and also like how actually we can build the leadership among the employees, and to make this becomes a data-driven way to do things. I believe this is going to be the future for the human resource management.
Yeah, I hope so. Any transparent, analytical, data-driven solution sounds like a good path to me. Well, Hui, thank you so much. I really enjoyed all the work your research group is doing. I look forward to seeing what else comes from you guys. And I'm grateful you came on the show to share your thoughts with the listeners today.
Yeah, thank you for inviting me to be here. It's my great pleasure to introduce my research work.
Excellent. Well, take care, Hui.
Yeah, bye-bye.
One quick announcement before we sign off. Santa Clara, California, November 4th through 6th, 2016 is the Open Data Science Conference West. I'll be there. I'm not presenting, just attending, but I'm looking to meet up with anybody from the data science listener base or data science community in general. I'm going to plan some sort of informal meetup. I don't have a location yet, but I'm going to give you a URL to keep checking. It's dataskeptic.com/ODSC. That's Open Data Science Conference. I'll post updated details there because these sorts of things can often have a last-minute change. That will be the official canonical place to find details about meeting up or hanging out or just getting in touch. Anyone who's there, be sure to come by. I'm giving out data science hex stickers, so come say hello. And until next time, I want to remind everyone to keep thinking skeptically of and with data.
For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.